Alright everyone, welcome back. In this video we will be talking about increasing and decreasing functions. We are in the point of the semester at which we'll be talking about some more applications of the derivative and what we can use the derivative for. In this particular section we will see how the derivative can be used to classify relative extrema, which we saw a while back, as either relative minima or relative maximum. Now, before we begin to define relative minima and relative maximum, we'll be talking about what it means for a function to be increasing or decreasing. So let's define those two terms right now. You may remember this from other classes, but if you don't, a function, in this case a function f, is increasing on an interval if for any two numbers, let's call them x1 and x2, on the interval, we have, let me fix this, we have that x1 is less than x2 implies f of x1 is less than f of x2, meaning that the order is preserved, the function preserves the order. Okay, so for example, let's say you have a function, let's say x1 is here, x2 is here. Clearly here x1 is less than x2. Let's say that f of x1 is here, so this is f of x1, and then now f of x2 is here. Clearly f of x2 is bigger than f of x1, which is higher. Okay, so that's what we mean by that. And 2, this is increasing, function f is decreasing on an interval if, again, for any two numbers x1 and x2, we have, on the interval we have x1 being less than x2 implies f of x1 is greater than f of x2. So what this means is the following. Again, we have, let's say we have x1 and x2. Now let's say f of x1 is here. Let's say now f of x2 is here. Well, here x1 is still less than x2. However, f of x1 now it's bigger than f of x2. So that's what we call a decreasing function. Now, in simple terms, a function is increasing if, as x moves to the right, its graph moves up, and a function is decreasing if as x moves to the right, the graph moves down. Okay, so for example, one of the easiest examples to talk about is simply the graph of y equals x. The graph of y equals x is a linear graph which looks kind of like this, so straight line. So this is 1, 1, 2, 2, and so on. So as the x values move to the right, meaning as you go from -1, 0, 1, 2, all the way to infinity, to plus infinity, the function values are going up at each step. So this function is increasing from left to right. I mean, this very clearly, if you just look at this from left to right, it's going up. As opposed to y equals -x, which is a reflection. This particular function now is going down from left to right. Okay, so this particular function is going down from left to right. So as you move to the right, as the x values are increasing, the function values are going down. So it's a decreasing function. Now, we have a test actually for increasing and decreasing functions. Because some functions that you will have, may not be as nice as this ones, and furthermore, sometimes you will just be given the in fact, most of the times you will just be given the equation of the function and not the graph itself. So if you're given the equation and not the graph, it may be actually very difficult to graph that particular function, at least in a timely manner. I mean, you could always graph a function. You can always graph a function. It's all a matter of the time that it will take you to. And remember, if it's a very long function, graphing by using the techniques such as creating a table could take you a very long time. In any case, let's talk about this theorem. This theorem is the test for increasing and decreasing functions. And this test, what it does is that it tells you when the function is increasing or decreasing on an interval. So, for example, before I begin, let me just do an example. I'll do it on this side in blue. Let's say somebody gave you a graph of a function. This function looked like this. This function is not going up throughout the whole graph. There are values for which the graph actually goes down, namely from here to here. So sometimes it's very useful to know what interval this corresponds to. Okay. Anyway, the theorem says the following. Let f be a function that is continuous missing a u there, on the closed interval ab, and differentiable on the open interval ab. The following things are true. If the derivative of f of x is bigger than 0 for all x's in the open interval ab, then the function f is increasing on the closed interval ab. 2. if the derivative of f is less than 0 for all x's, or remember when I say for all x's, I just mean for all numbers on the open interval AB, then f is decreasing on the closed interval AB. And 3, if the derivative of x is equal to 0 for all x's in the open interval AB, then f is constant on the closed interval AB. Remember, when we say constant, we just mean a horizontal line. Like, for example, y equals 3 is a constant function at 3, so it's a horizontal line. Okay. So let's do an example of how we can use this theorem to determine when a function is increasing or decreasing. Right, so example. Let's find the open intervals for which the function f of x is equal to x cubed minus 3 over 2 x squared is increasing or decreasing. All right, so first thing you should notice is that f of x is differentiable everywhere on its domain because it's a polynomial function. It's also continuous everywhere on its domain, which is, we really only need the continuous piece. Well, no, we need both, continuous and differentiable. So yeah, so f is both continuous and differentiable on the open interval minus infinity to infinity. Now, to actually figure out where the function is increasing and decreasing, we actually have to find out the critical numbers of the function. So let me just recall, we define critical numbers a while back. Critical numbers to be x values for which the derivative of x is equal to 0. So this is something that we did a while back. So we have to figure out when is the derivative actually equal to 0 to find these critical numbers. Well, let's take the derivative of f. F prime of x, by the power rule, is going to be equal to 3x squared minus the derivative of x squared is 2x, so we bring that 2 down. But the 2 is going to cancel out with this 2 in the denominator, so it's going to be negative 3x. So you have 3x squared minus 3x. We will actually factor this, so let's go ahead and factor. We will be left with 3x on the outside, and on the inside x minus 1. Now we simply need to find the critical numbers, and from this piece we know that the critical numbers are the values for which f prime of x is equal to 0. But we know what f prime of x is. F prime of x is 3x times x minus 1. So instead of writing f prime of x, I'm going to write 3x times x minus 1 equal to 0. So this is what we're interested in finding. By the principle of zero products, we know that this is equal to 0 when 3x is equal to 0 or when x minus 1 is equal to 0. If one of these is equal to 0, then the whole thing is going to be equal to 0. Well, 3x is equal to 0 precisely when x is equal to 0, because 3 times 0 is 0. And x minus 1 is equal to 0 when x is equal to 1, because 1 minus 1 is 0. So now we have found two critical numbers for f. So we have found two critical numbers for f. Now, an important question arises. This function f, I defined it to be on the entire real number line. Could there be any other critical numbers? Well, because there are no other points at which f is, for which the derivative does not exist, we can actually conclude that these are the only two critical numbers. Okay? So we only have two of them here. If you have, and we will see this in the future, if you have a function with a hole in it, where the derivative has a hole, such as a vertical asymptote, then we will consider that critical number as well when we are when we are testing for increasing or decreasing. Now, without further ado, let's actually figure out when the function is increasing or decreasing. I like to make tables, and I also like to determine my intervals. So I have two values. I have x is equal to 0 and x is equal to 1 as my critical numbers. I know that my function goes from minus infinity to plus infinity. That means that my function covers the entire real number line. So what should I do? Well, what I'm going to do is I am going to make three intervals. I am going to make the interval for the open interval from 0 to minus infinity, and I'm gonna minus infinity to 0, and then I'm gonna make the other open interval from 0 to 1, and then the other open interval from 1 to infinity. So I'm really dealing with three intervals. Like I said, minus infinity to 0, comma, 0 to 1, comma, 1 to plus infinity. These are the three intervals that I'm interested in. I have to find out what's happening to the function between these intervals. Is it increasing here? Is it decreasing here or increasing here? Is it decreasing here or increasing here? Okay, so how do we do this? Well, I just gave us some intervals, so let's actually make a table. So first of all, let's see, we have the intervals. Now, saying that you're working on the interval 0 to, minus infinity to 0 means that x is trapped between minus infinity to 0. That's what we mean here by picking this interval, that you're picking numbers that are only between minus infinity and up to 0, but not including 0. So that just means that we're dealing with numbers that look like this. X has to be bigger than infinity, than minus infinity, and less than 0 if x is to be on this interval. We're also dealing with the interval 0 to 1, so x has to be between 0 and 1. And finally, we have to have x be bigger than 1, but less than infinity. So these are the three intervals in question. The second thing that we need to do is choose some test values. This is, after all, a test. So I didn't tell you this was magic. This is actually a test right here. So we pick test values. These test values will be numbers of x that are found on these domains, on these intervals. You could pick any number you want. Like, for example, for the first one, I could pick -5, -1,000,000, -3,215, or I could just simply pick a simple number like, x equals -1. This is a simple number. For the second interval, 0 to 1, I could pick, 0.99999, 0.3278, 0.00053. All of these values are between 0 and 1. To make my life easy, I'm just going to make x be 1 over 2, 1/2, or 0.5. And finally, we have to pick a value between 1 and infinity, again, you could pick any number you want that's bigger than 1. To make my life easier, I will just pick x equals 2. Now, what do we need to do? Here is where the test comes in. The test says that if the derivative of x is positive for all x's on the interval, then f is increasing. I just picked a critical value, a critical number. I'm gonna plug it into the derivative and see what the sign of the number that comes out is. If it's bigger than 0, then we know it's increasing. If it's less than 0, we know it's decreasing. And if it's constant, then we know, if it's 0, we know it's constant. Well, what was the derivative? The derivative was 3x times x minus 1. So remember, f prime of x is equal to 3x times x minus 1. So if I'm working with the first one, which is minus 1, I have 3 times minus 1 times minus 1 minus 1. Well, 3 times minus 1 is negative 3. Minus 1 and minus 1 will give us negative 2. So this is going to give us 6. So we have here that the sign of f prime of x for this one, when we did f prime of negative 1, we have that is equal to 6, but 6 is a positive number. So we know that this is increasing. So in conclusion, and again, once you get better at this, you'll see that you will make this table much quicker than I'm doing it now. So in conclusion, we could say that on the interval negative infinity to 0, the function is increasing. So that means that it's going up from left to right. How about the second interval? Well, for the second interval, we have x is equal to 1/2. So we test using the derivative. Keep that in mind. I'm using the derivative for the test. I'm not using the actual function, the original function. In any case, this is going to be equal to 3 times 1/2 times 1/2 minus 1. Just plug it into the derivative. Well, 3 times 1/2 is 3/2, and 1/2 minus 1 is negative 1/2. Then when you multiply fractions, you multiply across, so 3 times negative 1 is negative 3, 2 times 2 is 4, so the solution is negative 3/4. So for the sign of f prime of x here, we have f prime of x, f prime of 1/2 is equal to negative 3/4, which is less than 0. So we know that on this interval, the function f is decreasing. Okay, it's going down. Finally, on the last interval, we have to test f prime at the value of 2. That means that we're doing 3 times 2 times 2 minus 1. Well, 3 times 2, last time I checked, that's 6. In fact, we got it from here. And then 2 minus 1 is 1, so the solution is just 6. So we have that f prime of 2 is equal to 6. 6 is a positive number, so in conclusion, we say that the function is increasing on the interval 1 to infinity. So now we can say that the function f is increasing on the intervals minus infinity to 0, and actually, yeah, I could say it together. So f is increasing on two intervals. It's increasing on negative infinity to 0 and 1 to infinity. This will make my life much simpler. And 1 to infinity. And f is decreasing on the interval 0 to 1. Okay, so this is the test for increasing and decreasing functions. This becomes extremely useful, again, in higher level math classes for those of you who will become math majors. There are times where, as soon as you get a function, if you take the derivative and you plug in the value that is of interest, you could clearly say whether the sign is positive or negative, and that will tell you whether the function is increasing or decreasing on the neighborhood that you're dealing with, and that can actually be extremely helpful. Before I end this section, let me actually give you some guidelines of how to go about finding intervals for which functions are increasing or decreasing. So guidelines for finding intervals on which a function is increasing or decreasing. Okay, number one, always locate the critical numbers of the function. So number one, locate the critical numbers of the function in the interval of interest, and use these numbers to determine test intervals. Okay, number two, determine the sign of the derivative, and I'll denote that by saying f prime of x at one test value in each interval. So at one test value in each interval. Number three, third thing we do is we use the theorem for the test for short, to determine whether the function is increasing or decreasing on the interval. Okay. Now, this theorem up here, the way that I wrote it, it's also valid when we write the endpoints as, let's say minus infinity to a, right? A to infinity, or minus infinity to infinity. This last example that we just did showed that, because I began by telling you that the function is defined on this entire interval, and then we actually broke it into intervals, into three different intervals, one going from minus infinity to some number a, one going from a number to another number, and one going from a number b, let's say, to infinity. We can see that the test worked at each interval. Okay, this is the so-called test for increasing or decreasing functions. If you're interested in finding more resources about this online, you are free to simply Google test for increasing or decreasing functions. That is the end for this part of the lecture. Thank you for your time.